Hello and welcome to the 19th session of the Introductory Biostatistics Distance Learning course. Today we're going to talk about multiple 2x2 tables. So you'll remember in the previous classes we introduced the concept of 2x2 tables or contingency tables. Then we discussed hypothesis testing and confidence interval construction for such tests. And remember, we went about analyzing these 2x2 tables in multiple different ways. We thought about tests for proportions first, then we looked at the chi-square test, and then we said, well, that depends on a normal approximation and requires large samples, so if we don't have that, we can do the Fisher's exact test. And then in the final lecture, the most recent lecture, I should say, we talked about the odds ratio and why that's a helpful measure for both cohort studies and case control studies. So today we're going to extend what we talked about to multiple 2x2 tables, but we'll start with a bit of a review to refresh your memory about where we are. So here's another example of a 2x2 table. So here we're looking at pelvic inflammatory disease, yes, no. And then ectopic pregnancy, yes or no. And then assessing whether there's a relationship between these two variables, okay? So if we were to construct the odds ratio here, in this case, the odds ratio, we would take 28, which is this number, times 273, divided by 6 times 251. 6 times 251. And that would give us an odds ratio of 5.08. So we always want to know what we mean by that. That's the odds of ectopic pregnancy among those who have pelvic inflammatory disease. Okay? So always want to keep in mind what it is that you're creating an odds ratio for. And then if we were to come up with a confidence interval for this, we could go through that as well. Okay? So suppose for some reason we were interested, instead of our usual 95% confidence interval, we were interested in a 99% confidence interval. Well, here in this case it would be from 1.59 to 22.1. Okay? So if we were doing a hypothesis test, hopefully you're thinking to yourself, well, we would reject the null hypothesis because the null value of 1 is not inside here. And so as a result, we would reject the null and conclude that there is a significant association between pelvic inflammatory disease and ectopic pregnancy. Okay, so what does that look like in Stata? We can take a look. So we just enter those numbers that we had there with this command, CCI. Here we've asked for a 99% confidence interval, and you can see it tells us the cases and the controls, the exposed and unexposed, and then it gives us the odds ratio down here. Here's our estimate, 5.075, the corresponding 99% exact confidence interval. And then here, just like we said, the p-value is less than 0.05, and we knew that because our confidence interval did not contain the null value of 1. Remember, an odds ratio, just as the name implies, is a ratio, and for ratios, the null value is 1. So since 1 is not in there, we know that we would reject our null hypothesis. Okay, so let's do another quick example, this time with an example from HIV. So if we're looking at HIV positive versus negative among people who use intravenous drugs versus those who do not, what does this relationship look like? Okay, so here are the numbers. These are the HIV positive folks over here if I can highlight them here, and then the HIV negatives are here, and then intravenous drug use, yes and no. Okay? So if we were to calculate the probability of being HIV positive, so the fitted probability of being HIV positive among those who use intravenous drugs, so the probability of HIV positive given intravenous drug use positive, that would be 61 over 136, okay? So 61 people both are HIV positive and use intravenous drugs out of a total of 136 intravenous drug users in our sample, and that turns out to be 0.449, which is 44.9%. And then if we were now to look at the probability of being HIV positive among those who do not use intravenous drugs, then we would have 27 here out of a total of 339, or 8%. Okay? And if we took the odds ratio, the fitted odds ratio, it would be 9.4. Okay? Okay, so we can go through our normal 7 steps of hypothesis testing here. So let's do that just as a refresher. So in step 1, we state our null hypothesis, which is that there is no association between IV drug use and HIV. Okay? And so in step 2, we talk about the type of data that we have. Here we have a binary outcome, which is, do you have HIV or not? And also a binary covariate, which is, are you an IV drug user or not? Covariate. Okay? So here, remember, we have several choices. As we mentioned, we could do a chi-square test, Fisher's exact test, or look at these in terms of a test for proportions. But we'll proceed with a chi-squared test. It looked like we had a pretty large sample size, so a chi-square test should be fine. Step 4, we have to write down our test statistic. This is obviously going to come from Stata. We won't compute this by hand. The chi-square statistic in this particular example is 87.5. Once we have our test statistic, we can get the corresponding p-value, which here is less than 0.0001. Okay? In step 6, we say that since the p-value is less than 0.05, namely it's even less than 0.001, we reject the null. Okay, and then in step 7 we write out our conclusion in words, which is based on our sample, there is a significant association between IV drug use and HIV status. Okay? So we'll talk a little bit more about this in a future lecture, but this is an association, right? This, what we've done here does not prove causation, right? It doesn't, we're not saying that being an IV drug user causes someone to be HIV positive, but instead that there's an association, okay? And like I said, we'll talk a little bit more about that in a future lecture. Okay, so that's a good review of where we've been with 2x2 tables. So today we're going to talk about what if, so far we've talked about just having one 2x2 table. What if we have multiple 2x2 tables? In that case, we want to do what we call a test for homogeneity, which is to say, are the different 2 by 2 tables that we have, are they homogeneous? Are they the same? Do they contain the same information? And then we'll do our normal kind of hypothesis testing and confidence interval estimation, as we always do. Okay. So just to remind ourselves of the big picture, remember we always want to think in terms of what types of variables are we dealing with. And here, since we have 2 by 2 tables, we're dealing with binary outcomes with binary covariates. Okay. But what we haven't thought about in this situation is, what if there are potential confounding factors that affect the relationship between our binary outcome and our binary covariate? Okay, so what are some examples of potential confounding factors, as I've called them? Well, it might be site. So if you do a really good study, you'll have multiple sites. Perhaps you're assessing something in Botswana, in South Africa, in Zambia, in Zimbabwe, and so on, and you want to see, are there differences by country or by site? Or even within Botswana, you assess something at different hospitals, and you want to see whether the effect is consistent for the different hospitals. Okay, so we need a way to account for the different hospitals or the different sites, for example, and see whether the effect is the same. Okay, so let's take a look at an example. This example comes from the Pagano and Gavreau book. That was one of the recommended texts for people who wanted to follow along using a textbook. So the example they use is, here CAD stands for coronary artery disease. Okay, so we're looking at the relationship between hypertension and coronary artery disease to see if there is a relationship. Okay. Whoops, I drew that line in the wrong spot. Sorry about that. Okay, so the relationship between hypertension and coronary artery disease. And the question we're asking is, does having hypertension increase your chance of having coronary artery disease? Okay, so the first thing we want to do is compute our odds ratio. And again, you always want to know, what is this odds ratio that you're calculating? So here we would take 1654 times 601 divided by, so you can see we have a very large sample size here, divided by 299 times 1959. Okay, and that gives us an odds ratio of 1.7. And again, we want to always know what it is that, because if we were to switch these labels around and we just went through the same formula, we want to know what it is we're creating the odds ratio for. So here this odds ratio is comparing people with hypertension, because hypertension falls in this box, to those without hypertension in terms of their risk for coronary artery disease. Okay, so what this 1.7, this odds ratio of 1.7 is telling me is that it appears that people with hypertension have more coronary artery disease than people without hypertension. Okay? All right. So, looks like there is an effect, and then we could construct a 95% confidence interval for this. The 95% confidence interval would go from 1.45 to 1.98. I'm not calculating that. That would come from software, so that would come from Stata. So hopefully you know the question I'm going to ask. So the question is, we have our estimate of the odds ratio of 1.7. We want to know, is it statistically significant? And the confidence interval allows us to answer that question. Since the number 1, remember when we look at odds ratios, the null value is 1. Since 1 is not contained in this confidence interval, we would reject the null and conclude that, yes, in fact, there is a statistically significant effect. Namely, people with hypertension have significantly more coronary artery disease than those without. Okay? So, that's what we've done so far. What we're going to do today is ask an additional question, which is, are there any other factors that may be related to heart disease? In other words, are there any potential confounders? Okay? So one potential confounder of this association between hypertension and coronary artery disease is age. Okay? We know that older people are more likely to have hypertension. We also know that older people are more likely to have coronary artery disease. Okay? So the study that we're talking about, for which we've displayed the results here, actually looked at two different age groups, those that were 35 to 49 and those that were greater than 65 years old. So let's look at each group separately, whereas so far we've only looked at the results combined. Okay, so taking a look at the groups separately, here is the table for those aged 35 to 49. Okay? And again, we're looking at hypertension versus coronary artery disease. Okay, so here the odds ratio, if we were to go through our normal calculation, would be 1.37, and the 95% confidence interval goes from 1.13 to 1.67. Okay? So it looks like there is an effect, namely people with hypertension appear to have more coronary artery disease, and not only that, it's a statistically significant association because our 95% confidence interval does not contain the value 1, the null value of 1 in this case. Okay? So again, that's for those aged 35 to 49. Okay? Now, what if instead, or in addition, not instead, in addition we looked at the older age group. Okay, what would they look like? Here's the older age group. So again, these are the folks who are greater than 65 years old, so age is greater than 65. The odds ratio here, if we were to carry it out, would be, the calculation out, it would be 1.32. So again, it looks like there's an effect. But this time, the 95% confidence interval goes from 0.97 to 1.80. Okay? So this time, the null value of 1 is in our 95% confidence interval. Okay? So we would conclude that, 0.97 is obviously pretty close to 1, and again, there's nothing magical about this alpha level of 0.05 that we choose, so we would say something probably like there's a marginally significant effect, okay? But this is, again, in the greater than 65 age group, okay? So the effect was 1.32, and the 95% confidence interval contained 1. Previously, for those aged 35 to 49, we had this 1.37, and the confidence interval here did not contain the value of 1. So the question we're asking now is, should we combine the odds ratios in these two different age groups to get one odds ratio, or should we keep them separate? So hopefully if you're following along, you might be a little bit stumped because, so if I display the results, you might be a little bit confused because we said overall the odds ratio, so this is the odds ratio, we said overall the odds ratio was 1.7. That was when we combined all the data that we had. Then we separated it into those 35 to 49, and we said it was 1.37, and then among those greater than 65, and we said it was 1.32. So how could it be that the odds ratio is higher in the entire population, 1.7, than in either of the groups, 1.37 and 1.32? This is something called Simpsons Paradox. Okay, we're not going to spend time getting into the particulars of this, but this is a good way that you can entertain your friends and family. You can tell them, I have a case where the odds ratio is higher in the entire group, in the entire population, than it is in either group. So you might be confused about that. But if you Google Simpsons Paradox, there's a nice Wikipedia page about it, so you can read more about it. We don't have time here to get into it. So the question that we're asking is, now that we have multiple 2x2 tables, right? We have two 2x2 tables in this case for the two different age groups. The question we're asking is, can we combine the information across the two tables? In other words, can I combine this 1.37 with this 1.32, or is there something different in the two age groups, and should I be keeping my odds ratio estimates separate? So that's our question, okay? Okay. So we're thinking about combining across tables, okay? So what would we want out of an approach that combines across multiple tables, okay? We would want the estimate to be a good summary of the tables. We would want the estimate to give more weight to tables with more information, right? So if I had lots more people aged 35 to 49 than I had older than 65, I would want my approach for combining them to give much more weight to the group that I had a much larger sample size for, right? Okay, and not only that, we want to be able to conduct some statistical tests to determine whether it's reasonable to combine our different estimates at all. Okay, so that's what we're going to talk about today. Okay, all right. So what is our approach? It's called the Mantel Hansel method. Okay, the Mantel Hansel. Let me see if I spelled that right. The Mantel Hansel method. Okay. So it's one commonly used approach when we're thinking about trying to combine tables. Okay. So what do we do in the Mantel Hansel approach or method? First, we calculate the estimated odds ratios. The estimated odds ratios in each group. Okay. So in our example, we had the younger age group and the older age group. Then in step 2, we have a statistical test if the estimated odds ratios are similar, if they're similar enough to combine. Okay? And then in step 3, if it's reasonable to combine, then we do so, then we combine. If it's not reasonable to combine, in other words, if they contain different information, there's a different relationship for the older people versus the younger people, then we report individual odds ratios. Okay, so that's our basic approach here. All right. So we do this thing called a test for homogeneity. That's the Mantel-Hansel method, okay? And the test in step 2 is the test for homogeneity. That's just a fancy way of saying we want to test if these different odds ratios are homogeneous or the same, whether they can be combined, whether they contain the same information. That's a test for homogeneity, okay? So what would the null hypothesis for a test for homogeneity be? Well, it would be that the odds ratio in group 1 is equal to the odds ratio in group 2 is equal to the odds ratio in group 3 is equal to ... the odds ratio in group K, depending on how many groups we have. In our example, we only had 2 groups, so we would stop here But again, this can be extended all the way up to k different groups, okay? And so what would the alternative hypothesis be? Hopefully you remember this from when we talked about ANOVA, or analysis of variance, okay? Remember, we had a very similar null hypothesis. It wasn't in terms of odds ratios. It was the mean in group 1 is equal to the mean in group 2 is equal to ... the mean in group k. And you'll remember the alternative hypothesis for ANOVA was that at least one mean is different, right? So we have the same construct for our alternative hypothesis here. We say that at least one odds ratio is different, okay? All right. So what does it mean if we reject the null? Here, that would mean we're saying, hey, we don't believe this null that all the odds are different. So if we reject the null, what we're saying is the estimated odds ratios are significantly different. Okay? All right. And in that case, we would have to report different odds ratios for the different ages for our example. Okay? All right, so now I'm going to show you a bit of technical results about this test for homogeneity. Again, don't worry about the particulars of the formula. Just think about how the formula can help you understand the concept that we're talking about. Okay? So this is a technical piece about our test for homogeneity. Okay? All right. So here are the formulas. Okay? So in order to perform the test for homogeneity, we use a chi-square test. That's why we have this chi-squared here. Okay? So this yi down here, that's our estimate of the odds ratio in each group, right? In our example, we would have y1 and y2, where y1 is those 35 to 49, and y2 is those greater than 65, okay? And then this wi here, remember we said we want to give more weight to the ones where we have a larger sample size so that we have more information, okay? So that's what this wi is doing, okay? This is 1 over the variance, okay? So when we take 1 over the variance, what we do is we're giving weight, we're giving more weight to the estimates with lower variance, okay? So higher weight to lower variance. If we have lower variance, that means we're more sure of our estimate because we have a larger sample size, for example. So if we have low variance, we want to give those estimates high weight because we're very sure about them, okay? And then here, this gives us the, sorry about that. This gives us the average odds ratio weighted based on the variance, right? That's where the W weights are coming in, okay? So we use this formula to give us the average odds ratio if we've determined that it's okay to combine, okay? So again, don't get lost in the technical details. All you want to take away from this is, hey, we're doing a chi-square test to see if our different odds ratios can be combined. These are our different odds ratios. We give them different weights depending on how much information and how sure we are of our estimates. That's this piece, 1 over the variance. And then if it's reasonable to combine, we do so using this formula, which takes the weights into account. Okay? So that's what we want to get out of that slide. Okay, so let's try it for an example of coronary artery disease and hypertension in these two different age groups. What would that look like? Okay, so here's the 35 to 49 group. Here's their the log. Remember we talked in the last lecture about why we take the log of the odds ratio because of the nice properties of the log. It when you have a ratio, it becomes a subtraction. So the log odds is 0.31, and this W again is the inverse of the variance. It tells me how sure I am about this estimate. It's 104. Okay. So now what would it look like for those greater than 65? That's here. Okay, so these are among those greater than 65 years old. And the log of the odds is 0.28. And then my measure of how sure I am is 43.8. This means that we have a lot more information in the, because the W for the 35 to 49 group is larger, 104 compared to 43.8. What that means is I want to give more weight to my estimates from the 35 to 49 group because look, these are the numbers that I have in the different cells of my table. 552 in cell, 941, 212, and 495. While it's true that I have 1,000 in one group here and another 1,000 in a different cell in my 2x2 table for those greater than 65, the issue is I have two cells with only 87 and 106 people, which is why we're giving more weight to our estimate from those aged 35 to 49. Okay? All right. So from there, we can continue with those formulas that we were looking at earlier, right? So our combined odds ratio, which we called Y, the combined odds ratio would be here, okay? And the test statistic, the corresponding test statistic, the chi-square test statistic is here. Okay? All right, good. So, what do we need to do? We need to do the test for homogeneity. We have our combined odds ratio. Remember, this is for the log odds. We have our combined odds ratio, but we still haven't answered the question about whether we think it's reasonable to combine these two different groups and get one odds ratio. So that's what we have to do now. So let's do our test for homogeneity. And go through our same 7 steps for hypothesis testing that we always do. So here we would have that the odds ratio in group 1, those 35 to 39, is equal to the odds ratio in group 2, those greater than 65. And obviously the alternative here would be that they're not equal. Remember, if we had more than 2 groups, we would have to say at least one of the groups is different. But here we only have 2 groups, so our alternative is just that they're not the same. In step 2, we talk about the type of data that we have. We have an odds ratio outcome and a binary predictor. The binary predictor is, are you in the 35 to 49 age group, or are you in the greater than 65 years old age group? Okay. The appropriate test here is this homogeneity of odds ratios test. The corresponding test statistic, again, we would get this from Stata. We wouldn't do this by hand, and we obviously magically wouldn't know it. Stata would tell us that the chi-square value for this case is 0.04. The p-value, which again we would get from Stata, that corresponds to this test statistic, is 0.83, so a large p-value, much larger than 0.05. And so since 0.83 is larger than 0.05, we fail to reject the null. We fail to reject the null. Okay, remember our null was that the two odds ratios were the same. So we fail to reject that null. And in step 7, where we state our conclusion in words, we would say, remember we usually say, based on our sample, there is no significant difference in odds ratios by group. So as a result, we can combine. We can combine the two odds ratios into one. Okay? So that's our test for homogeneity. Okay? So now that we've determined, yes, in fact, we can combine these the two different odds ratios for the two different age groups, now we have to think about how to combine these. Okay, how can we combine our two different odds ratios into one? Okay, so remember we already have a combined estimate for the log odds. That was that formula for this variable that we had called y. Okay, let me see if I can find that. Here it is. Okay. Remember the W's were the weights. We wanted to give more weight to the estimates that we were more sure of. And here was our, this is our estimate for the log of the odds ratio. We discussed in the previous lecture about why we work with the log of the odds ratio. Okay? And so if we want to get back to the actual odds ratio, instead of the log of the odds ratio, we take e to the log of the odds ratio. We know that exponentiating, this e, exponentiating is the opposite of the log. Okay? So these things cancel themselves out. So e to the 0.303, which is the log odds, if we exponentiate that, we get 1.35. That is our estimate of the combined odds ratio. Okay, and this is remember we already saw this guy Wolf. This is Wolf's combined odds ratio. Okay, so there's our estimate, 1.35. That's the combined odds ratio. We conducted a test for homogeneity. We failed to reject. We said, hey, it looks like we can combine these odds ratios, and so we did. And here's our 1.35. And hopefully by now you're very familiar with this setup. We know that just an estimate of the combined odds ratio is not enough. We need an estimate of its variance so that we can construct confidence intervals and do statistical tests. Okay, so how do we get a standard error for the combined odds ratio? Okay, so the combined estimate standard error is based on the sum of the standard errors of the two individual odds ratios, just as you might suspect. Okay, so what we want to think about in this case is how to combine these different odds ratios. So how do we do that? What does the formula there look like? Here is the formula for combining the standard errors. So this, again, is just that the combined standard error, remember we had called that y, is just a sum of the individual standard errors, which are the w's. Okay? So now that we have an estimate of the log odds ratio and the standard error, we can construct a confidence interval. Okay, so using the normal approximation as we typically do, we can construct a confidence interval for the combined log odds using the following expression. Okay, remember, hopefully this is very familiar to you now. Here's our estimate of the combined log odds ratio. Here's our critical value. It looks like here, remember we usually write z over 1 minus alpha over 2, but we know 1.96 is the critical value for constructing a 95% confidence interval. and then times the standard error, comma, estimate plus critical value times standard error. Okay, so very much a familiar format for the construction of confidence intervals. And so therefore, in this case, in this particular example that we're working with, remember we need to exponentiate because our estimate is for the log odds. So if we exponentiate both sides, we can then get a confidence interval for the odds instead of the log odds. Okay? So remember, this is all trying to get us to be able to answer this question: is there a significant association between hypertension and coronary artery disease in our combined sample? Excuse me, so here's our confidence interval. Our confidence interval does not contain 1. 1 is not in there. And as a result, we know that we would reject the null and conclude that yes, in fact, there is a significant association between hypertension and coronary artery disease. Okay? All right. So there are other estimates of the odds ratio. Remember, we used the Wolf combined odds ratio. There's also a Mantel-Hansel approach with this variance estimate that comes from Robbins and others. So we're not going to worry about the particulars of that, but we just want to know that when we go into Stata, it's going to give us different estimates for the combined odds ratio and its corresponding 95% confidence interval. So we just want to be aware of that. Okay, so there's also this Mantel-Hansel approach. Okay, so let's take a look at what that might look like in Stata. So here's some Stata output. Remember, so in our data set here we have CAD for coronary artery disease, hyper for hypertension. We want to weight it by frequency, right? We want to give more weight to the tables that we have more information or more study subjects from. And then we're looking at by age. Okay, so here age 0 and 1 correspond to those between 35 and 39, and those greater than 65. Okay, so here we get an odds ratio in each group. Here are the two separate odds ratios. We have the corresponding 95% confidence intervals for them separately. And then here we get our Mantel-Hansel combined odds ratio, okay, which is 1.35. You can ignore this crude one. We get the corresponding 95% confidence interval for the combined odds ratio, okay? But again, before we even get to this question of whether we can combine, we have to do this test of homogeneity. Here's the test statistic for the Mantel-Hansel test for homogeneity, and the p-value was large, so we failed to reject. Remember, the null hypothesis was that the odds ratio in group 1 is equal to the odds ratio in group 2. We failed to reject, so we say based on our sample this assumption seems reasonable, and so we do combine, and that's where we use this 1.35 as our estimate and this corresponding 95% confidence interval. Okay? And so you can see in this combined confidence interval, 1 is not contained inside there. And so our conclusion after all that work is we can say, hey, we can combine these two different age groups, and once we do combine them, we see that there is a significant relationship between hypertension and coronary artery disease. Okay? So again, there are these different ways of calculating the confidence intervals. There's the Mantel-Hansel method, there's the Wolf method. Here we have a fairly large sample size, so they'll agree in terms of the conclusions. Okay. Alright, so we want to remember our goal is not to worry about the different approaches for these estimates and their confidence intervals. Instead, what we want to focus on is how to interpret, to understand the interpretation of when to combine and and when a combined odds ratio shows a significant effect. Okay, so a combined odds ratio shows a significant effect in the same way that a single one does, namely if the confidence interval does not contain our null value of 1. Okay, so now that we've combined, we can do this hypothesis test of whether the combined odds ratio is different than 1. So this was kind of step 1. We wanted to see whether the odds ratios were equal. Then we said we could combine them, so our second null hypothesis is that the odds ratio combined is that significantly different from 1. Okay. And remember, for a single table, we used the chi-square statistic, which took the observed counts in each cell of the 2x2 table, subtracted the expected count, squared that, and divided by the expected. Well, how can we extend that for multiple tables? So again, just to be clear, we're now in this step 2. We've combined our odds ratios because we determined, hey, it was okay to combine based on this p-value. And now we want to ask the question, is our combined odds ratio significantly different from 1? And we want to extend the chi-square method to multiple tables. Okay, so now we're working with multiple tables, and we want to know how can we combine for this null hypothesis that the combined odds ratio is equal to 1. Okay, so again, now I'm going to show you some formulas. Don't worry about the particulars of the formula, just think about the concepts here. Okay, and so basically what we're doing is another chi-square test, right? There was the observed minus the expected, and here we're using these weights, right? We want to give more weight to the estimates that we're more sure about. Okay, and so those letters inside there kind of whoops, sorry, that got really busy. The letters there kind of correspond to these things, okay? So when you see this A and B and C and D, that comes from our 2x2 table, remember, that we looked at before. And M1 and N1 were the totals and so on, okay? So again, don't worry about the particulars of the formula, just we're just thinking about the concept here, okay? So now we can do our 7 steps of hypothesis testing, but now this time we're testing the null that the combined odds ratio is equal to 1. Okay, and obviously the alternative would be that it's not equal to 1. Okay, the type of data that we have is the odds ratio outcome with a binary covariate. We're going to conduct the Mantel Hansel test. Our test statistic, which we would get from Stata, it turns out in this case it's a chi-square value equal to 13.67. The corresponding p-value for that test statistic is equal to 0.0002. Then we compare that p-value, 0.0002 is less than 0.05. So therefore we reject the null hypothesis. And then in step 7, we write our conclusion. So we would say that based on our sample, we conclude that there is a significant association between hypertension and coronary artery disease. So significant association between hypertension and coronary artery disease. Okay? So that is our conclusion. Okay, so what does this look like in Stata? Again, because we can do these first 3 steps without Stata, write out our null, talk about the type of data we're dealing with and the type of tests we have to do, but steps 4 through 7 require output from Stata. So what does that output look like? Here we go. So again, coronary artery disease, hypertension, we want to give weight by the frequency. We want to give more weight to the ones where we have a larger sample size. We're splitting it by age. Okay. We get the odds ratios in the 2 different groups, the corresponding 95% confidence intervals, and then here's the, we've already decided that we could combine. We decided that based on this p-value from the test of homogeneity. So now we're looking at the combined odds ratio, which is 1.35. Here's that corresponding 95% confidence interval. Here's the Mantel Hansel test statistic is 13.67. The p-value is 0.002. That's the p-value being less than 0.05 corresponds with 1 not being inside this 95% confidence interval, right? And so that's why we concluded that there is a significant association between hypertension and coronary artery disease. Specifically, those who are hypertensive tend to have more coronary artery disease. Okay. So let's do another example to kind of really drive this idea home. So suppose we have a placebo-controlled clinical trial with 3 different sites. Okay. So there might be 3 different hospitals within Botswana, for example. Okay. So at each site, we plan to enroll 100 patients. Okay, so we wanted 100 at 3 different sites, but for logistical reasons, it turned out that we got 90 at site 1, we got 120 at site 2, and we got 104 at site 3. Okay, and in this trial, we're looking at this dichotomous or binary outcome for the occurrence of brain lesions on MRI, okay? And we want to conduct our analysis controlling for these 3 different sites, sites 1, 2, and 3, okay? Okay, so let's take a look at what our 2x2 table would look like for site 1. Remember, we have these 3 different sites. So here's site 1. Okay, this is site 1. Okay, and we're looking at our treatment versus placebo. And we're looking at whether people developed lesions or not. Okay, so this is site 1, and if we carried out the odds ratio estimate for site 1, it would be 0.36. And the corresponding 95% confidence interval, which we would get from Stata, goes from 0.14 to 0.92. Okay? So again, this would be significant because 1 is not contained in there. Okay? Now, what if we were to add the results of our experiment for site 2? Here is site 2. Okay? The odds ratio estimate for site 2 is 1.29. The 95% confidence interval, let me just erase this part. The 95% confidence interval goes from 0.55 to 2.99. So you can see these 2 sites have told us very different things, because here in site 1 the estimate of the odds ratio was less than 1, and here it was greater than 1. So those are conclusions in 2 opposite directions. But notably, the estimate of site 1 was significant because the 95% confidence interval did not contain 1, whereas the estimate for site 2 was not significant because the confidence interval did contain the null value of 1. Okay? So what does the site-specific odds ratio for site 3 look like? Here is that table. This is site 3. So the odds ratio in group 3 here is 0.28, and the corresponding 95% confidence interval goes from 0.11 to 0.67. So this looks like site 1, right, where we had an odds ratio less than 1, and it was significant because the number 1 is not contained in here. Okay? So let's take a look at these all together to see what it looks like. So here's the odds ratio in these different sites. Okay, so site 1, 0.36. Site 3 was also less than 1, but we had this weird thing here in site 2 where it was greater than 1. Okay, so it appears that based on the individual odds ratios, it seems like the effective treatment was different at the different sites. So our question is, should we combine these 3 different sites? Okay. So what do we want to do? We want to conduct a test for homogeneity. What we've learned about today. Okay. So the null hypothesis, remember we can do our 7 steps of hypothesis testing again. The null hypothesis is that the odds ratio at site 1 is equal to the odds ratio at site 2 is equal to the odds ratio at site 3. Remember, importantly, the null or the alternative hypothesis is that at least one odds ratio is different. Okay, so the type of data that we're working with is an odds ratio outcome with now it's a categorical predictor, right? Since we have more than 2 groups, we have 3 groups. We have a categorical covariate. Sorry, my handwriting's getting worse. So the test we're going to do is this homogeneity of odds ratios test. The corresponding test statistic. Remember, these first 3 steps we can do without Stata, but starting in step 4 we need our output from Stata. The corresponding test statistic here from Stata is equal to 8.33. The p-value that goes along with the test statistic of 8.33 rather, is 0.016. Since 0.016 is less than 0.05, we reject the null. Okay, we reject the null that the odds ratios are the same. Remember, that makes sense based on what we saw. Remember, site 2 looked like it went in the opposite direction. So in step 7, we conclude that there is a significant difference in odds ratio by site. Okay? So what do we do now? We've concluded that there is a significant difference by site. So now what we have to do is we say we cannot combine the odds ratios. So now we're going to report individual estimated odds ratios because it's not reasonable to combine. So in other words, when we write up our paper, we would say, here's the odds ratio at site 1, here's the odds ratio at site 2, and here's the odds ratio at site 3. We couldn't combine them because our test for homogeneity was significant. Okay? So we report these different odds ratios, and then we want to think about why did we get these different estimates. Excuse me. So we might investigate if there's a covariate imbalance across the different sites that could have caused the difference in odds ratios. For example, perhaps there were more women enrolled at one of the sites and the treatment was less effective in women. That could be one potential explanation. So you could say that maybe site 2 had more women and the treatment was less effective in women, and that's why we saw that difference in site 2. Okay, so that's where you have to go the extra mile and really think about why there was this difference in your data. Okay? All right. So let's that summarizes or concludes, our approach for multiple 2x2 tables. So let's just summarize by talking about our analysis plan. So when we have multiple 2x2 tables, we first calculate the odds ratio in each group separately. Then we do this test of homogeneity. We test if the odds ratios can be combined. Then in step 3, if the odds ratios can be combined, which is to say, if we get a p-value greater than 0.05 for our test of homogeneity, which means that we think it's reasonable to combine the odds ratios. So if the odds ratios can be combined, then we obviously calculate the combined odds ratio. So maybe I should call this 3A and 3B. If the odds ratios cannot be combined, so that happens if we conduct our test for homogeneity and we get a p-value less than 0.05, we conclude that the odds ratios cannot be combined. We then report individual odds ratios, and we want to think about possible explanations for why we got different effects at different sites or what have you. Okay, so I'll stop there. That concludes our treatment of multiple 2x2 tables, and I will see you in the next session.